In this presentation, we discuss complex numbers. And the reason that we're going to talk about complex numbers is because as we're analyzing AC circuits in the time domain, where we have currents that are functions of time, sinusoidal, and voltages, which are functions of time in a sinusoidal way that may not be in phase with the current, it's not really practical to try to think about adding two sine functions that have different phase angles or dividing and so on. It just becomes very complicated to do it that way. And so it's actually more practical to write these voltages and currents and express them in phasor notation. And then using that phasor notation, we can actually write those phasors in terms of these complex numbers that we're going to talk about. And we're also going to be able to talk about other types of circuit elements and write them as complex numbers, such as impedance. And just to, we haven't talked about impedance yet, but impedance is basically going to be something that's similar to resistance when we talked about DC, and it measures how much that component resists the flow of electrical current in a circuit. And so we can use these representations for the phasors in terms of the oscillating sources that are in phasor notation. We can represent those as complex numbers and also these impedance values. And it's going to make analyzing AC circuits much easier. So before we talk about what a complex number is, we need to go back and refresh our memories about imaginary numbers. And an imaginary number is basically one that has the square root of a negative number. So for example, if I had the square root of negative 100 and I tried to put that in my calculator is going to say I can't do this because it's not real. So in terms of real numbers, which is what our calculator usually deals with, there's no way to calculate that. But there is a way to use complex numbers and imaginary numbers in the complex plane. So in order to write this imaginary number in a different way, we can take 100 and we can say, well, 100 is the same thing, or negative 100 is the same thing as negative 1 times 100. And then I can take the square root of that, and I can separate the square roots out. So I could take this as the square root of minus 1 times the square root of 100. Of course, the square root of 100 is just 10, but I still have this square root of negative 1. And the square root of negative 1 is an imaginary number. So we want to find a different representation for that square root of minus 1. And in mathematics, we use the fact that we have this imaginary number, the square root of negative 1 is represented as I. So anytime you have something and you say, well, this is a negative number, you can use this I, and that's the representation for the fact that it's imaginary. So the problem is that in circuits, we use I to represent current. So we have to have a different notation. So in circuits, we actually use J to represent an imaginary number, specifically the square root of minus 1. So we could rewrite the square root of negative 100, which is just 10 times the square root of minus 1, where the square root of minus 1 is just j, and we could write this as j times 10, or 10 times j. It doesn't matter what order you do it in. And that's telling me that this is actually multiplying 10 by this j is an imaginary number because j is the square root of minus 1. So how is that related to a complex number? So a complex number is actually made up of a real number and an imaginary number, and it has a form that is represented by, we're using C here for the complex number, and so the real part here does not have any imaginary part. There's no j associated with it. And then there's also an imaginary part to this complex number where b multiplied by j is a complex number. A and B in this formula actually are real numbers. So the fact that this is a complex number comes from the fact that there's a real part of this complex number, which is A, and then there's an imaginary part which is represented by the B multiplied by the imaginary part. So all complex numbers can be written as a real part plus an imaginary part. And very similar to vectors, we wouldn't add the x component of a vector to a y component of a vector, and you can think of these as components to this complex number. And so as such, we can actually represent a complex number in rectangular form and in polar form. So a complex number is represented as a point on a two-dimensional plane that's called the complex plane. So this is very similar to vector notation with an x and a y axis, but instead of an x-axis, we have the real axis. The positive real axis is to the right, and the positive imaginary axis is in the vertical, the upward vertical. And so if I had a complex number that had a real part of 6, I would go across the real axis and I would go 6 over, and it has an imaginary part of 8, so I would go up the imaginary axis 8, and I could represent that particular complex number as a point in the complex plane. It's very similar to a vector that had an x component of 6 and a y component of 8. But these are different things. I can't add those two quantities together because one is real, one part of this complex number is real, and one part is imaginary. So you might remember back to vector notation, and so this is the rectangular form of the complex number, where the components of the complex number, the real and the imaginary pieces, are separated from one another. We could also represent this as a vector with magnitude and direction in this two-dimensional complex plane, and we call this the polar form. And so this same exact complex number, this point in space, can be represented as some distance from the axis of the complex plane out to that point in space, and some angle that it makes with respect to the real axis. And so you probably could kind of guess to some extent how you would figure out from this point right here, from this complex number, how you could figure out what the polar form would be. What is the length of this vector right here? And since I have a right triangle, I can figure out, the sides of that triangle and use Pythagorean's theorem. And then if I want to know the angle, I can use my trig functions. So here are, here's my vector notation, my polar form, and then here are the components that I would have had over here. And I should be able to go between these two very easily from what I know about vectors. So here's my same picture from the previous page, more general terms. So my complex number has a real part and an imaginary part. So here's my real part A, my imaginary part, the B here. And I can represent this in rectangular form, which is A plus JB, or I can represent it in polar form, where it has some length associated with it here, and I can find that length by using Pythagorean's theorem, a squared plus b squared, square root, and some angle with respect to the real axis, and I can find that angle by taking the tangent inverse of opposite over adjacent. And so now I have a way of going between the rectangular form and the polar form. If I have the polar form and I want to go to rectangular form, I use the fact that I have a right triangle, and I can find the adjacent side here, the real part, by taking the magnitude times cosine of the angle, and I can find the imaginary part, the opposite side, by taking the hypotenuse times sine of the angle. So in general, I can write this complex number as the real part, which would be A, which is c times cosine of the angle, plus the imaginary part, which would be c times sine of the angle. So all complex numbers can be written in both rectangular form and polar form. So what happens if you only have a real part or you only have an imaginary part? What do the angles look like here? So if I only have a real part and it is a positive number, let's say that my complex number only has a real part 1, that means that it's lying on the real axis, and so my angle would be 0. If I had a complex number that was -1 and it did not have any imaginary part, then it would lie on it and it would have an angle of 180 degrees. So some of these, it's a good idea just to remember that if the complex number only has one part associated with it, you just have to sort of identify what those angles are. Here I have an imaginary part only, so my complex number is just 1 times j, And so this lies on the imaginary axis, and so the angle is 90 degrees. And if it was minus j, so on the in the negative imaginary axis, it would be negative 90 degrees. Or you could use 270 degrees as well. So in this particular example, we're going to start off with this complex plane, and we have these different points in the complex plane, and we're going to determine what the complex number is, and we're going to do that in rectangular form and polar form. So we start off here with C, and we realize that that point on the real axis is at 4 and the imaginary axis is 3, so I can write that as 4 plus j3. I can then calculate what that complex number is in polar form by figuring out what the hypotenuse is. It's the square root of the component squared. And I can determine the angle. So the opposite side is 3, the adjacent side is 4. I take the tangent inverse and I get 36.9. And so I can write that complex number in rectangular form and then also in polar form. And then you should notice that in polar form it's looking very much like our phasor notation, and that's what we're going to use a little bit later. So now we can look at our next one. I think the next one we're going to do is D. So if I look at my complex number D, which is in the complex plane, it's on the real axis 4, the imaginary axis negative 4, so I can write that as 4 and then a negative imaginary part. I can also determine what the polar form is. So I look here and I can figure out what the length of that vector is, the square root of the component squared. And I can determine the angle. Now, just like with vectors, you do have to be careful when you're using the inverse tangent of the components. So this is inverse tangent of the opposite side, right? So this is the imaginary part, which is negative 4, over the real part, which is 4. I get negative 45 degrees. That makes sense because it's below the real axis, and if you remember in phasor notation, that would be a negative angle. So I could write that as 5.66 times as the, not times, but 5.66 as the actual length, and then an angle of negative 45. All right, so the next one we're going to look at is this point here, W. And we're going to have to be very careful as we look at W, because remember that tangent is positive in the first quadrant and in the third quadrant, and it's negative in the fourth quadrant and the second quadrant. So let's just see what happens here if we're not careful. So the complex number has a real part that's negative, negative 4, and an imaginary part that's positive 4. Right? And then I have my point in space that I'm interested in finding. So when I use Pythagorean's theorem, take the square root, I get 5.66. That's basically just the opposite of what I had over here for point D. Now, when I take the inverse tangent, I have to be very careful, because if I actually put the values in and I put a negative 4 over 4, I would get a negative 45 here. But I realize that the angle that I'm actually getting when I put those values in, and if I use positive values, the opposite side here has a length of 4. The adjacent side has a length of 4. And so I'm actually figuring out what the angle here, I've called it phi, is 45 degrees. That's not the angle with respect to the real axis. So when your complex number is in the third quadrant, or excuse me, this is the second quadrant, is in the second quadrant or the third quadrant, and you're solving for the angle, you really have to think about what angle you're measuring when you get the value that your calculator spits out. So the actual angle I'm interested in is this angle here, and of course this angle would be 180 minus 45, which is 135. So the complex number w should be represented as 5.66, and the angle would be 135 degrees. So very careful. It's a good idea to draw a little picture of your complex number if you're not sure, so that you know which quadrant it's in. And then the last one is this point right here. And this one is pretty straightforward because it's on the negative imaginary axis. So I could just write that as negative j times 2. It doesn't have a real part. If you wanted to put the real part in, you would just say it's 0 minus j2. And so I realize that the magnitude of this vector is just 2. That's the length of it. Right here, that's the length. And then if I want to know the angle that it makes with respect to the real axis in my picture is negative 90. So I'm not using the formulas, I'm just using what we talked about earlier in terms of if you have a strictly real part or a strictly imaginary part. And so I would write that imaginary number as 2, and the angle would be negative 90. Or I could write this as 2 with an angle of 270. So if I went the other way around, it's the same thing as 270. Sometimes we will see situations where we have the imaginary number squared or cubed or raised to the 4th power. And it's good to know some of these, but these are things you could also calculate on, as needed. But if you have an imaginary number, just the j piece squared, that's the square root of negative 1 times the square root of negative 1, which actually just gives you negative 1, because that's negative 1 squared. If you have the imaginary part cubed, you could always separate this out as j squared times j. J squared is negative 1, so that's a negative j. If you have j raised to the 4th power, that's a j squared times a j squared. Each of the j squareds are minus 1. Minus 1 times minus 1 is a 1 again. And that pattern starts to repeat itself. So if you had j to the 5th, it would be a negative, j to the 5th would be a positive j, and then it just kind of starts repeating this pattern again. If you have a negative j times a j, that's a negative j squared. J squared is negative 1, so that becomes a positive 1. Of course, that's just like saying you put a minus sign in front of this, so it's the same thing. We also might have a situation where we have 1 over a j value. So to figure out what this is, we need to get rid of that j on the bottom. So we would multiply the top and the bottom by a j. This gives us a j at the top and a j squared at the bottom. The j squared is a negative 1. The negative 1 can be on the top or the bottom, so it's a negative j. So 1 over j is the same thing as a negative j, or a negative imaginary part. These are just powers of j. It's something that you might want to reference later on. It's not super important right now, but I just wanted to mention that you do have to be a little careful when you're multiplying imaginary numbers, that you really think through how things are being multiplied, and also especially when you're dividing.